In this section, we're going to focus on inverse functions, and we have fallen back a little bit to section 7.7 to pick up the ideas of inverse functions, and then we're going to apply them in section 8.3 to the ideas of logarithms and inverse functions. So we're kind of having a mix of sections here with a unique order, but I hope this will be helpful as you work through this. So we've talked about before inverse functions, and basically when we're talking about logarithms versus exponential growth, we know already we're going to switch the x and the y intercepts. The 1, 0 in a logarithmic graph switches to 0, 1 in an exponential graph. But to switch two functions, very simply, we're going to switch the x and the y values. Once we do that, we're going to solve for y. And when we're finished solving for y, we're going to label our new function as y inverse or as f of -1 of x. Now, I don't need to get worried about this. This little -1 does not mean an exponent. It just very simply means an inverse function. It's a new notation. Much like if you said someone was 4 foot 10 inches. The 1 tick mark and the 2 tick marks mean feet and inches. Well, if we're talking about degrees, minutes, and seconds for longitude, latitude, you might have something that's 35 degrees, 4 minutes, and 10 seconds, which refers to a location in the world versus feet and inches. So we just have to keep context in mind. This is not a -1 exponent, but this is an inverse notation. So let's try this on our first problem. I'm going to write each of our original problems in blue, so y equals x squared plus 1 in blue. Then in green, I'm going to switch the x's and the y's, so x equals y squared plus 1. Now I'm going to take my x equals y squared plus 1 and solve for y. So I'm going to bring over the 1 and get y squared, and then I'm going to take the square root and get the square root of x minus 1 equals y. I'm going to finish up by writing my final problem with inverse notation. F of inverse of x equals the square root of x minus 1, or we could write this as y inverse equals the square root of x minus 1. Very likely in this case, because we start with an f of x, it's going to probably finish with an f of x on an answer guide or a solution set. Let's look at example 2. Once again, let's write the original equation as y equals 2x minus 4. Now we're talking about a line, 2x minus 4, versus the original one was a parabola. Let's change to green and change the x's and the y's. So we have x equals 2y minus 4, and now we are into our inverse. To solve this, we add 4 to both sides, and then we divide both by 2. So here's the final result of our inverse. So I'm going to write this in red. Inverse of f of x equals 1/2 x plus 2. Or, once again, we can write it as y inverse equals 1/2 x plus 2. So here's another example, but now we're in a line versus an exponential parabola situation. Our third one is exponential. We have 3 to the x, so that's y equals 3 raised to the x as our original function. Switching the x's and the y's, we have x equals 3 to the y. Now we're going to bring in the ideas that we talked about yesterday, where we're taking a logarithm and an exponential function and we're reversing the two. I'm just going to come off to the side here and remind us, in our original problems, we had ideas like this. Y equals the log of base b of x, and that led us to a transformation back and forth of I think it was x equals log base b of y is how we originally said, which leads us to b to the x equals y. We're going to use this transformation idea to transform this problem and get the y by itself. So let's go back to green. The 3 is our base, and so we're going to have log base 3, but now we're going to take the log of the x instead of the log of the y like we have over here, and this equals y. So our inverse function is inverse of f of x equals log of x base 3. And the inverse function, you'll notice we're going to take the base is the same, but we're going to take the log of the answer and that is going to equal the exponent. So over here we have the log of the answer in the problem below equals the exponent of x. So, or, as you know by now, you could say log of 3 base x is equal also to the inverse of y. Let's practice one of these now with a little bit more on an exponential form. And so here we go. We've got y equals 5 to the x minus 2. I like to put those exponents in parentheses, plus 1. First, we've got to isolate that exponential form. And so we're going to switch the x's and the y's, and then we're going to start the problem. X equals 5 to the y minus 2 plus 1. We bring that 1 over. I'm going to put it in parentheses. And now we have b is 5 raised to the exponent, the y minus 2, equals our answer. To transpose this, or to transform it, we're going to say the same base, so log base 5 of the new answer, x minus 1, equals our exponent, y minus 2. And to finish this out, we say log of base 5 of x minus 1, and then we're going to bring over that 2 equals y. So to write this with function notation, f of negative 1 equals the log base 5 of x minus 1 plus 2. Could we also say this is equal to y of negative 1? We certainly could. So inverse y would be another option to write that as. That's kind of an algebraic approach. Now what I want to do is look at a graphical approach and talk about our functions with regards to domain and range. Domain and range are just two other names, as you know, for x and y. So on each of our next problems, we're going to kind of take a graphical approach, and we're going to take the parabola from example 1, and we're going to plug in 3 points, 0, 2, and 3. So first we plug in 0, and we get 0 squared plus 1, which is 1. And this gives us the point 0, 1. Now we're going to plug in 2 and 3. 2 squared plus 1 equals 4 plus 1, or 5, which gives us the point 2, 5. Lastly, we have 3 squared plus 1. That equals 10. That gives us the point 3, 10. Now let's compare this with the square root of x minus 1, which we realized on the first problem was our inverse problem. So here we have the square root of x minus 1 is the inverse of x squared plus 1. So when we plug in the value 1, we have the square root of 1 minus 1, which is the square root of 0, which is 0. So we have the point 1, 0. Now we try it for 5 minus 1, which is the square root of 4, which is 2. So we have the point 5, 2. And lastly, we have the square root of 10 minus 1, which is the square root of 9, which is 3. So we have the point 10, 3. And I hope you can see that our blue points from our original function x squared plus 1 are the exact inverse of our green points from the inverse function of x minus 1. So that's just an example of how points can demonstrate something as an inverse as well. Now, by now you've probably realized that all of these inverses are symmetric. And they're symmetric over the line y equals x. And so I can't emphasize enough drawing this line to help see your symmetry in our problems, and that's what we're going to do on our next function. Let's plot the points that we've just talked about above of x squared plus 1. So we're going to plot these in blue, 0, 1, 2, 5, and 3, 10 is off the graph. But we do know with a parabola we do have a pattern 1, 1, 2, 4, 3, 9. So 1, 1 brings us to there, 2, 4 brings us up to 5, and then we can be symmetrical going the other side as well. So here's our basic parabola going up. Now, next we're going to draw the line y equals x. So here's the line y equals x. It has a slope of 1 with a y-intercept of 0. That really is a dotted line, so I'm just going to try to make it dotted here, just for reference, because it's just a reference point. Then, on the other side in red, I'm going to plot the points that are symmetric. So 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. Negative 1, 2 becomes 2, negative 1. 2, 5 becomes 5, 2. And negative 2, 5 becomes 5, negative 2. And so here you can see the parabola is symmetric to the blue parabola, but now it's sideways over that dotted line, y equals x. If we think back to example 2 from above, we had the line 2x minus 4, and the inverse to that was 1/2 x plus 2. So let's try these graphs here. 2x minus 4. Let's plot that first in blue. Go down to negative 4 and do a slope of up 2 over 1. And I'm going to draw a blue line through those points, trying to keep my slope exactly at that value. Let me try that again here. Here's my point. Stretch it out so our slope is right on the money at 2, 1. Okay, now second, let's take and draw the line y equals 1/2 x plus 2. Well, we're going to start at 2 with a slope of 1/2. You see we do have an intersection point there at 4, 4. And let's draw that line now, going through our points. Stretch out our slope there. And then finally, let's draw the line y equals x. And what you see when you draw the line y equals x here is you see now with lines, it also is a perfect symmetrical approach to our problem. I am dotting my green line because it really doesn't exist. It's just a reference point. So we can see our blue line and our red line are really symmetrical to each other. The inverse was in red. The original function was in blue. And I think it's, do they look symmetric? I think the simple answer is, of course they do. Okay? It's hard to say that they don't look symmetric with lines. It's very simple to see that. All right, let's move to the next page, and let's graph the inverse of an exponential function. By now, you know that the inverse function of a growth part is going to be very simple, going through 0, 1 as our point. We're going to sketch that same line, y equals x. So here we have y equals x. We're going to make that dotted. And now we're going to draw the inverse function versus our original function of y equals 3 to the x. Our inverse function, as you can imagine, is going to go through the point 0, 1, because 1, 0, 1 flips to 1, 0. And then it's going to curve away from the dotted green line, much like the blue line curves away. And like this one comes down to the x-axis, our exponential graph will come down to the y-axis. And so there is our inverse function of our graph. The equation for this inverse function would be simple to find. Okay, we can practice doing that again. Our original function is y equals 3 to the x. So we interchange the x's and the y's. So x equals 3 to the y. And now we transpose that. The log of our answer to the base 3 equals y. And so what is our inverse function? Very simply, inverse function is the log base 3 of x. And that's what that function is right there. And you remember we did that before, and you just got to remember you're transposing the inverse after you switch the x's and the y's. Now we're going to try a couple quick examples explaining how to find an inverse of our function. So let's take a look at some of these down here. Our original function, obviously I'm going to just circle that or box that in blue because we don't need to rewrite it, but that's our original function. We're going to keep our same pattern, and now in green I'm going to switch the x's and the y's. 2x minus 1 plus 3. Step 1, bring over the 3. Step 2, square both sides. We're not going to have to worry about going to standard form here. We're perfectly fine with taking this and going into just our vertex form. So now I'm going to add 1 equals 2y. And then finally I'm going to divide both parts by 2. or multiplying by 1/2. So there's our final function. So we can write this in red. The inverse of y equals 1/2 of x minus 3 squared plus 1/2. Now, characteristics of this graph, I hope you will very quickly see that the characteristics of this inverse are right 3 and up 1/2. So it would be easy to graph this parabola just going right 3 and up 1/2. Okay, let's look at our example 2. I'm going to box this in blue with recognizing the fact that is our logarithm. Now we're going to switch the x's and the y's, which gives us x equals the log base 4 of y. Now we're going to transpose that. Here we have 4 raised to the answer equals y. So we start with a logarithm, which leads us to an exponential. And hopefully you're starting to see that these are inverses of each other. So my inverse function is merely 4 to the x. And I think you can realize by now that a logarithm and an exponential growth are inverse functions of each other, which is why when you get these, they should look very similar to our problems, especially when it comes to inverses. All right, let's look at our third example here. I'm going to box our original problem because that is my original function. And then we're going to take it and exchange the x's and the y's to get the inverse. So that becomes a y minus 2 plus 1. I think you're realizing by now you've got to isolate that logarithm. I'm going to put parentheses around here, realizing that x minus 1 is together. Now we're going to take the base and raise it to the x minus 1, and that equals what's inside the logarithm. And so we bring over the 2 as our final step, and that equals y. So let's write this with inverse notation. Inverse of y equals 2 raised to the x minus 1 plus 2. Which way is this shifted? It's shifted to the right 1 and up 2. Anyway, there's a couple examples of what it does to take an inverse function of a problem. Our problems tonight are right down here on the bottom. We've kind of copied them over for you. We have a couple from 7.7, finding inverses, and then a couple from 8.3, finding the inverse of a logarithm. So the same process on both, just two different functions to work with. I hope this has been helpful in understanding inverses.